All right, this is my second or third attempt at recording this video. Hopefully the dogs won't start barking this time. All right, we're going to do section 11.1, and the learning targets are really important today because basically you need to be able to describe data as skewed left or skewed right, and is it symmetric? You need to be able to find the mean, median, mode, range, and standard deviation of a set of data, and calculate the 5-number summary and graph a box plot. So some of what we do is not necessarily stuff that you're going to be assessed on. So I am going to go kind of fast through some of these. All right, this is something you do need to know. You need to know whether data is symmetric or skewed. So these are histograms. So in other words, the data points were put in and broken up by category. And usually if the data is symmetric, it doesn't have to be this shape. Okay, symmetric could even mean, that it went like this. Means that somehow there's some kind of symmetry, but this is the most common symmetry. This would be like a bell curve shape. And so the mode is always the tallest bar here, the most often occurring data point. So the mode is the same as the mean and median when it is symmetric, if it's perfectly symmetric. But if the mode and the mean and median are close, we still call it symmetric, okay? If some data has, if the mode occurs over to the right, and what we call the tail is dragged to the left, it is called left skewed or negative distribution, okay? The mean is less than the median and the majority of the data is on the right, but the tail extends further to the left. All right, so we describe where the tail is. So a positive or right skewed distribution means the tail has been dragged off to the right. So the mode is over here, but the median and mean would be dragged further to the right. So the mean is greater, and then the median and the majority of the data is on the left, while the tail extends far to the right. So more of the data is over here, but the tail is dragged off to the right. Since standard deviation just measures the spread of the distribution, the statistic is also non-resistant to the effect of outliers, okay? So the standard deviation is not so affected by outliers. So this leads us to this guideline. If the distribution is symmetric, we use the mean and standard deviation because it's free of outliers, okay? If the distribution is skewed or has strong outliers, it's better to use the 5-number summary. All right, so we need to get that in our brain because that's going to take us through the rest of the lesson today. If it's symmetrical, we can stick with mean and standard deviation. If it is skewed, then we need to use the 5-number summary, okay? And I think this is on the top of your notes worksheet. Same thing, it says here, reasonably symmetric, mean and standard deviation are all you need. If it's skewed, it's messed up a little bit, skewed left or skewed right, or called negatively skewed or positively skewed. Again, that refers to the tail. Then you got to do the bigger 5-number summary. All right, so this is a lovely set of data about the number of passengers who boarded airplanes in 36 different airports in 1 year. Not something I want to have to type into my calculator, so I'm just going to run through their example. It says construct a histogram. So what you do is you type all these data points into the stat list. So stat enter, put them all in, and you don't have to do that for this example. Then you would go to turn your stat plot on. So second y equals, and turn plot 1 on. But what you want to pick for a stat plot for the type is this one that looks like a bar graph, okay? This is a histogram, and then whatever list you had it in, okay? And then you would do a zoom stat. Now they did that and they got this where a whole bunch of data is on the left and there's just a few things over to the right. So the tail points to the right, so it is positively skewed or skewed right. When it is skewed, you are not to use the mean and standard deviation. Instead, you're to use the 5-number summary. So you would say, I'm using the 5-number summary because the data is skewed or skewed right. The number of passengers ranged from, and they used the max and the min, and the median number was, okay, and half of the airports had between, and then they used Q1 and Q3. Maybe? Oh, actually, yeah, that's what they used. Okay. So that's a 5-number summary written out as a sentence. All right. So some restaurant advertises that they have a 20-pound sirloin steak on the menu. The weight of the samples of the steaks is shown. So I typed all these bad boys in, and you can certainly pause the video and do that. It would be good practice. So stat, enter, put all these in list 1. Then it says summarize, construct a histogram. Okay, so I have mine in list 1. So I'm going to go second y equals, turn plot 1 on, but I need to meanwhile turn plot 2 off because I have it on as well. Okay, let's just do this. All right, now my plot 2 is off. When I go second y equals, plot 1, on, histogram, list 1, just to make sure, I'm going to go stat enter. These are all the steaks in list 1. Okay, so then I'm going to do a zoom 9. And here's my histogram. Now, the median, the mode, the highest bar is definitely right here in the middle. By the way, if you go to your window, when you do a histogram, it's taking the minimum and maximum, and it sets some kind of a scale up. The scale is how wide your bars are. So if I go back here and I trace, this says from 17 to 17.8 ounces, there was 1 steak. From 17.8 to 18.6, there was 4 steaks in that range. Now that's kind of a funky setup, so I might have put 17 and 22. Oh, that's not a 22. And said I'm going to count by ones. In other words, 1 ounce differences. And then you could look, okay. Again, this isn't really drug out particularly one way or the other. If I had changed this to like a 0.5, oh, I didn't change it, did I? Just kidding. Okay, so I don't think it's particularly skewed one way or the other. The other thing I did to check that is I went and did the 1 variable stats, and the mean was 19.3, and when I scrolled down, the median was 19.5. So I decided those were close enough together for there to not be any significant skew one way or the other. Okay, so I said since it's fairly symmetric, the mean and standard deviation are okay to use. The mean weight of a steak was 19.3 with a standard deviation of about 1 ounce. And again, that information came from doing the 1 variable stat. The mean here is the X bar, and the standard deviation was the S of X. Okay. Moving on. It says distributions of data are not always symmetrical or skewed. Sometimes they fall into clusters or subgroups. If a and it could also be what's known as uniform. This is an example of just uniform data. In other words, each category had the same number of people or number of data points. If a distribution has a gap in the middle and there are two separate clusters, it can be what's called bimodal data. And they give us a quick example of that here. The annual cost of tuition for a sample of 20 colleges at a college fair showed up this way. So they put in the data points and did a histogram, and it turns out that there was two separate equal, there was a whole bunch of data around here. There was what we would call a mode here and a mode here. Bimodal data, meaning there was two most often given answers, or in this case, costs. The histogram, the distribution is neither symmetric nor skewed, but it's called bimodal. It's the cost of colleges. Can anybody think why the cost of colleges would be in two separate categories here? I'm thinking these would be like public universities and these would be private colleges or private universities. They would have significantly greater costs involved. All right. So since the data is bimodal, an overall summary of center and spread given each is inaccurate, so it would be better to separate it. Okay. So they separated it, sorry, at the bottom here it said the mean of cluster 1 was about $11,000 with a standard deviation of about 4, where for the mean of the second cluster was almost 32,000 with a standard deviation of about 3,000. So significantly higher costs in that second set of data. All right. Box and whisker can also be used to determine the shape of a distribution. You have to look closely at these because if the left whisker is longer and the line representing the median is closer to Q1, then it's called negatively skewed. Okay, so the median and everything over here to the left is the tail longer to the left. Symmetrical, it's about the same. And here the right half of the box and the right whisker are longer, so this would be called skewed right or positively skewed. And the 5-number summary is for skewed data, and it's also for making the box and whisker plot. Remember, we talked about this already, that 25% of the data is here, 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 here. Okay, but this is more spread out. So the data between the median and Q3 are significantly more spread out than the Q1 to the median. So even though it's 25% of the data points, they were further apart. All right, the difference is called the interquartile range. We talked about this. It's the width of the box. So from Q1 to Q3. So for this example, 7 to 10 would be a difference of 3. That would be the interquartile range. All right, the quartiles, blah, blah, blah. We already did this. So here's our example. A shoe store employee designs a display by placing shoe boxes in 10 separate stacks. The number of boxes in each stack are 5, 7, 9, 11, 13, 10, 9, 8, 7, 9, 8, 7, and 5. Right. This is weird data. I don't know why you care about how many boxes are in each stack, but it says construct a box plot and use it to describe the shape of the distribution. I would like us to do this by hand once real quick to make a box plot, because I want to show you how this works. So I just put them all in order. Everybody see what I did? Let's make sure I got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there's 10 data points. So the middle one, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The middle of the data is here, so the median is actually halfway between, or 8.5. So 8.5 is our median. Now, the min is 5, and the max is 13. That seems pretty easy, pretty self-explanatory. But the quartiles, I just want you to understand how those are found. Of these 5 data points, you find the middle of those. And so 7 is Q1 because it's the middle of the bottom half. And of the top half up here, the middle data point is 10, which is Q3. So our box would go from 7 to 10 and have whiskers out to 5 and 13. Now, this looks pretty symmetric to me. I tried to make my line even. This whisker is a little bit longer, so this whisker is 2 units long and this whisker is 3 units long. But it's not significantly skewed. So I did do it on the calculator as well and did turned this stat plot on to a box plot. I can show you that real quick. So I don't know if I have these data points in. I'm pretty sure I do somewhere. I think they're over here in list 5. Does that look like our shoe boxes? So if I turn this on, I would want to go back and put this fourth choice over is our box and whisker plot that will show any outliers. And mine is in list 5, and then I'd want to do a zoom 9. So it doesn't have any outliers, and my box halves look really similar. This whisker is just a tiny bit longer, so it's quite symmetric. If it's symmetric, we don't need to do the 5-number summary. We can do simply the mean and standard deviation. So then we would go stat, calculate, one variable stats. It is list 5. I don't know how I managed to have that in there. But the mean is 8.4 boxes in a stack with a standard deviation here of 2.5. So I hope that's what I wrote at the bottom. Since this data is pretty much symmetric, the mean and standard deviation will work. The average number of boxes in a stack was 8.4 with a standard deviation of 2.5 boxes. All right. The interquartile range determines an outlier. So that's where you subtract the quartiles and then you multiply that difference by 1.5 and you add and subtract it onto Q1 or Q3. We did this yesterday, but again, I said you won't have to calculate this. You can either, on a quiz, I believe there's a question that says, how do you know if it has an outlier? Well, it's okay to say one of the data points was more than 1.5 times the interquartile range beyond the box, or you can simply say, I graphed it on my calculator and it showed that one of the points was an outlier. Okay. The overview is neither whisker can be more than 1.5 times the length of the box. All right, I'm on to worksheet 11. It says the ages of Oscar-winning actresses from 2 20-year periods are shown. Construct side-by-side box plots of the 2 data sets, then use the display to compare the distributions. So I'm not going to do this on my calculator, too much work, but they put all of these in. So from 1969 to 1988, they got this top box plot, okay? There were 2 outliers in the data. Looks to me like these 2 were outliers. No, that's not it either. Well, actually, there are 3 outliers. I think all 3 of those points were considered outliers. Everybody else fell between, 21 and 49, I think. And then this half, or this set of data was from 1989 to 2008, still really old data, but this time around, it shows that there were 2 outliers, and they were again on the older end of the data points, okay? And everybody else, it looks like, fell between, who's the youngest here, 26? And do we have any 50s? 49? All right, so when they graphed them one above the other, which you would put this in one list and this is another and turn them on in like plot 1 and plot 2, and then just do a zoom 9 and it would compare the two. It says from the graph we can see the median age, the middle line here, for the first 20 years is just slightly higher than the median age for the second. The range of ages for the middle 50% is greater for the actresses from the second. So this difference, remember when I threw the outliers out, I was doing from minimum to maximum, so the length of the whole thing. But they say if you look at the box here, the width of the box is much more concentrated here, and it's a little more spread out here, okay? So the range of ages for the middle 50% is greater for the first set. Both data points have outliers greater than the rest of the data. Ignoring the outliers, the distribution for the second set is more symmetric, okay? Now, if I asked you to write a summary, everybody could have something a little bit different, and that would be okay. All right, now I actually did put this data in. If you want to pause the video and do it, you can, but it says the average wind speed recorded at various weather stations in the United States. So I put them all in one list, okay? And when I put them all in one list, I got here a mean of 9.2, a standard deviation of 1.6, and this was the plot that I got, okay, for a box plot. So it looks very symmetric. Now, I did do the histogram because that's actually what the question asked for. So let me get rid of this guy. It says, construct a histogram. Now, I have two shown here because when I just did the zoom stat, this is what it gave me. But when I looked at the window, it was really wonky. It's cutting off every 1.26. So I also redid it, setting the window up to count by ones. And then this is what it looked like, okay? I really don't think either one of those is particularly skewed. Okay, this one especially kind of looks like, you know, the mean and median would be close to the center. All right, so it says summarize the data using either one based on your synopsis. I said since the data is not skewed, the mean wind speed of 9.2 miles an hour and standard deviation of 1.6 miles an hour are fine to describe this data. Okay, so it said summarize it, and we didn't need the 5-number summary and all that because it was symmetric. Now, they go on and use this data. Question 4 says that there are stations near the ocean and stations that aren't. Now, if you want to do this on your calculator, I moved some of the data points, okay? Because I don't remember what all that they had, but New Orleans is on the Gulf, so I considered that near the ocean. I looked up where Atlanta is a middle state, is not an ocean state, an oceanside city, so I moved some of their data around. But when I did that, so I went through, let me just show you on the calculator. I did stat, enter, and let's see, I put in list 2, Albuquerque, Dallas, Kansas City, okay, cities that aren't near the ocean. Since I'm doing this, I'm going to be brave and delete this list. We're not talking about those. All right, so we're talking about list 2. Those are not the ocean. And then in list 3, I put Baltimore, Los Angeles, okay? Now, I would have thought there would be a significant difference between the wind speed near the ocean and not, but it's an average wind speed for the city, and I don't know, like, I don't think all of Los Angeles is right on the ocean, if you get my drift here. So, anyway, when I put them in, if I turn on a stat plot, I think that's what I'm supposed to be doing. So go over to this guy for list 2. The blue, I guess we could change the color quick. Yeah, I didn't on mine, so I'm just gonna leave it. The blue is list 2, which is actually not the water. That's why I was going to change it to a different color. And then I go down here and I turn this one on and make this still a box and whisker, but list 3. Okay. And then I do a zoom 9. Whoops, zoom 9, Hochbauer. This is what I get. Okay. Now you will notice the median for both is very close. Okay. Even with the outliers, it's kind of hard to tell much significant difference. So I went down here and I said the average of the wind speeds in cities near or not near the ocean doesn't seem to be much different, but the spread is much wider for cities near the ocean. So here, they're far more spread out than here. Even if we ignore the 2 outliers, it doesn't really do much other than extenuate here, even that this is far more spread out. And I messed around with this a little bit and tried like throwing a couple cities out and it didn't do much. All right, moving on. Last little section of the lesson today is on percentiles. In addition to quartiles, you can use percentiles to indicate the relative position of an individual value within a data set. So percentile divides a distribution into 100 equal groups and are summarized by this P, like P99 would be the 99th percentile. A percentile graph uses the same values as a cumulative relative frequency graph, except the proportions are used instead of percents. All right, what is this talking about? Well, if you have 10 students whose GPA is between 2 and 2.5 and 28 students who are between this and this, and you want to compare, okay? So you don't just want to know what your GPA is, but you want to know where you compare to other students. It says the graph gives the frequency of the distribution of GPAs of 200 students at Ashland School. Be very, very, very careful. Percentage is not percentile. So if you get an 85 out of 100 on a test, you have an 85%, but that doesn't mean you're in the 85th percentile, because it doesn't mean, is not indicating how you performed compared to the rest of the class. It could be that your 85% was in the 40th percentile. Maybe everybody did better than that. So percent and percentile are not the same thing. So here's the information from Ashland School. So what they do, there were 10 students in this lowest group. So that was 10 out of the 200 students, or 5%, had below a 2.25. So you go over to 2.25 and they put it 5%, the dot. Then you have to add these two together. So the cumulative frequency up to 2.5 was 38 students. And 38 out of 200 is 19%. So below a 2.5 was 19%. That's where that dot came from. Then they added up all of these, and 68 students had 2.75 or below. So 2.75, they're over at a 34, and so on. Okay, 100 students total had below a 3. So at 3, it's up at 50%. And so on. So the question is, was there a question? I thought there was a question. Okay, so maybe it's on the next slide. Estimate the percentile rank of a GPA of 3.4. So if somebody had a 3.4 GPA, it's just below the 80th percentile. So it says here a GPA of 3.4 is better than about 78% of the students at Ashland School. All right, so we're going to do a real quick percentile graph, and I started us out here. It says the scores are the frequency distribution of the scores on a test. So 3 people scored between a 55 and a 60.5. So that's 3 scores, and I totaled these up and there were 37. And 3 out of 37 gave me 8%. When I did 3 out of 37. I got 8%, okay? So over here, that was everybody below a 60.5. So at 60.5-ish, we're at 8%. Then it is cumulative frequency. So I have to add these two numbers together, and that's 11 students are below here. So 11 out of 37 is almost 30%. So we use the right-hand side here. So at about 66, we're at 30%. So, sorry, I lost my cursor. What's happening here? So at 66, I should be up at 30%. Did I not write that down right? 11 out of 37 was 30%. Okay. So when I tried to do this earlier, I had the dot in the wrong place. All right. If I add 12, I am up to 23 students. If I add 5, I'm up to 28. If I add 9, I'm up to 37. So this would be 100%. But 28 out of 37 and 23 out of 37. I need to calculate here. Yeah, that didn't go well, did it? All right, so I had 62 and 76 we'll go with. See if I can remember that. 62%, 76%, and 100%. All right, again, we're using these. So at about 70, we were up to 62. At 76, a score of 76, we were up to 76%. And at a score of just over 80, we were up to 100%. So if I were to try to connect those, and we know how that goes when I try to draw a straight line. So something like this. All right, then it asks, estimate the percentile rank of a score of 62. So if someone had a score of 62, looks to me like their percentile might have been just below 20%. I'm going to write the word percentile, not percent. I'm trying to keep those clear. So a score of 62 would be about the 18th percentile. So not very good. If you want to be above the 76th percentile, top fourth of the class, you had to score above a 76 on this particular test. All right, so the assignment on this is just to do a few little questions, and a couple of them are calculator practice, and this 11 through 14 is just a quick 4 matching questions. And that is on the bottom of 11B. That's it, guys.